The next thing we want to do is take the angular momentum theory that we covered in the control volume analysis section of the course and apply it to a centrifugal pump. So this is just revisiting the centrifugal pump, so let's remind ourselves how this works. This is the suction side, so the fluid is coming in here along the axis of rotation. This is the impeller, which is rotating around that axis. The fluid quickly turns and travels in the radial direction as it interacts with the impeller blades, and then it leaves the impeller out here and is collected in this scroll area, and then that's connected to the discharge. Turn this 90 degrees so the axis of rotation is right at that spot, and it's now perpendicular to the screen. And we see the impeller blades here. The fluid is entering at this point in the center of rotation, then turning and traveling radially outwards and leaving the impeller, collecting and going out the discharge. So we're going to do a control volume analysis on the impeller. So we're going to go through that in detail. So this is zooming in on just the impeller. This impeller is turning in the clockwise direction. And I've shown just a single impeller blade, but of course there would be many blades on this typically. But we're just going to show one to do this analysis. So it's a control volume analysis, so we need to identify what is our control volume. So the inlet of the control volume is going to be this cylindrical surface. So I've shown a red dotted circle there, but the surface that the fluid is entering our control volume through is actually a cylinder. So imagine that circle protruding in and out of the screen a certain distance, and the thickness of the impeller in that direction, perpendicular to the screen, is an important parameter that we're going to bring into the analysis later. So there's a cylindrical surface there, and the fluid is crossing that surface and entering into the control volume. So flowing radially into the control volume through that surface. So it comes into our control volume, then it interacts with the blades that are in here. We're going to talk lots about that, but eventually it leaves our control volume, and the exit of the control volume is out there. So again, this is a cylindrical surface. We're just seeing it in cross section here. It protrudes in or out of the screen a little bit, and again, the thickness of the impeller out there typically would be different than the thickness of the impeller here, but that's another parameter that we'll see show up in the analysis. So both this inlet surface, which I've labeled 1, and the exit surface, which I've labeled 2, are cylindrical surfaces. So that defines our control volume. So we want to apply conservation of angular momentum to the control volume. So we have our conservation of angular momentum equation here, and we want to apply it to this control volume that we just defined. So we're going to go through these terms one by one and see what stays and what goes. First, we need to establish a coordinate system. So right at the center of this impeller, just putting that dot there, is the origin of our coordinate system. And the z-axis is going to protrude into the screen from that point. So we have a z-axis pointing into the screen from that point. So that means this impeller is turning in the positive k-hat direction. And we could put an xy coordinate system on there, but I'm not going to bother cluttering this up. The important axis is the z-axis because we're looking at rotation around that z-axis. So it's the k component of this equation that we're interested in. So we're interested in moments around that point and rotation around that point. So now we can consider each of the terms in the conservation of angular momentum equation. First of all, we have the torque, or the moment created by the body force. Well, we're going to neglect this. We're basically assuming that this is homogeneous, so there's not going to be any net turning effect around the center here, or it'll be very, very small anyway. The next term here is the pressure force, and this one is interesting. The entire purpose for this pump, of course, is to make the pressure at 2 bigger than the pressure at 1. So we certainly can't say that we have a uniform pressure on our control surface. The pressure is definitely different at the discharge than it is at the inlet. So there is certainly a pressure change from the inlet to the exit. So we need to think about this term carefully. However, realize that this is not a force, it's a moment or a torque. This is the moment that the pressure forces produce around our axis of rotation. And of course that's going to be zero, because if we look at the pressure on the outside here, P2, doesn't matter where we go on this surface, we draw all these pressure forces. They're all perpendicular to the surface because they're pressure forces. They have to be perpendicular to the surface. And they all pass through the origin. Okay? So even though there is certainly a pressure on the outside of our control volume, there's no moment because the R cross N is zero everywhere on this outlet. And so that's what makes that term zero. It's not that the pressure is small, it's because R cross N is zero. And the same thing happens if we look at the inlet. Okay, so if we look at the inlet instead, everywhere on the inlet the pressure forces are perpendicular to the surface. Well, they all pass through the origin. So this entire term can be neglected because the R cross N is zero everywhere. The next term is the moment due to the viscous forces. So these are shear forces on the surface of our control volume. Now in reality these will not be zero. There are certainly viscous shear stresses in this fluid that could be important. However, those are very, very difficult to quantify, and they will be taken care of when we determine the efficiency of the pump, probably experimentally. So in terms of this analysis, where we just want to get at the major terms of this equation that are in play here, we're going to be neglecting these viscous forces. So of the assumptions we've made so far, this is the weakest one, but the concept of pump efficiency will take that into account when the time comes. So the only thing we have left on the left-hand side is any torque that is applied to our control volume by any solid object that is cut by our control surface. Now, this is an example of a case where our very greatly oversimplified sketch of the apparatus makes it look like that's zero, because we look at our control surface and we say, well, it doesn't cut any solid object. But remember, control surfaces are three-dimensional things. They have to completely enclose the control volume that we're looking at. So because this is just a 2D representation, our control surface just looks like two circles. But of course those circles have to connect in 3 dimensions. So somewhere that control surface has to cut through the impeller or the shaft that is turning the impeller. So if we were to look at this thing 90 degrees, maybe the impeller looks like this, and it's got a shaft connected to it that's going and connected to a motor. Our control volume, in addition to looking like that, has to enclose this entire thing, and so right there it has to cut through a shaft. This impeller isn't just floating in space with no connection to the outside world. Our control volume has to cut through it. So we do have to keep this term because our control surface does cut through the shaft. Next, on the right-hand side of the equation, we have the unsteady term. Well, we're just going to analyze steady-state operation of this pump. So certainly there is some angular momentum inside of our control volume. That is certainly not zero. But for steady state, the fact that this term is the derivative of that quantity with respect to time means that this is zero, and we can ignore this term. So that leaves us with a term that accounts for the transport of angular momentum across the control surface. So at each the inlet and the exit, we're going to assume that there's uniform flow. So we know that this term then will reduce to just the mass flow rate times the R cross V at each of the inlet and the exit. So with all of those assumptions applied to conservation of angular momentum, we get this. So torque is the only term left on the left-hand side, and that has to be balanced by the mass flow rate times R cross V at the exit, which we labeled 2, minus R cross V at the inlet, which we labeled 1. So notice that because there's just a single inlet and a single exit, the mass flow rate has been factored out here because it's the same for both of them. So now we want to take a look in detail at these two terms, and we're going to look at this one first. So we're going to focus on what's happening at the exit of the impeller blades and figure out what this R cross V is. So to do that, we're zooming in on the impeller. So we're going to be working in this region here. So remember, this is the inlet. So the water is entering radially here, and then it's moving along the blade and exiting out here at the outlet. So we're going to be working in this area for a moment, which is the exit. So the first thing to realize there is that the water is going to be traveling along this blade. So we're going to think first of all about the velocity of the water as it leaves our control volume, in other words at that point, but relative to the blade. Well, that velocity is going to be tangent to the blade because the water has to travel along the surface of the blade and leave the control volume. And remember, there's blades periodically all the way around. So that's true everywhere along the exit. So we call that VR2. So it's the velocity relative to the blade, relative to the control volume at point 2. Now that's okay, except that the velocity in our momentum equation, so the R cross V that we're trying to calculate, this velocity is an absolute velocity, meaning relative to an inertial frame of reference, so it can't be rotating. So because this velocity is tangent to the blade, it's going to make an angle beta 2 with the circumference of this circle. So notice this beta 2 is a physical feature of the impeller design. It's this angle here as well. So that's one of the parameters that a designer of impellers would really be paying attention to, is what do they want that beta to be. So the thing we need to remember though, that's a physical feature of the impeller, so a design feature of the impeller. Now in order to get the velocity of this relative to the ground, we need to add to it the velocity of this point on the impeller. In other words, the velocity of our control volume. Well, that is going to be omega R2. So remember, our center of rotation is down here somewhere. So this point is traveling in that direction at a speed of omega R2. R2 being the distance from there to there. So it's tangential velocity omega R2. So we need to add these two together to get the actual velocity of V2 relative to the ground. So we just do that with the parallelogram law. So I'm just shifting this vector over here and adding it to that. And so the resultant will be V2. And that's the velocity we're really interested in. So if you were standing out here, stationary, in other words, just standing on the ground watching the water come flying out of here, this is the velocity you would see. And that's the velocity that needs to go into the R cross V term. So that's what we're interested in. What we're going to do is break that velocity into two components. So this line is tangent to the circumference of the circle, and that angle we're going to call alpha 2. Notice, unlike beta, alpha is not a physical design feature of the impeller. It depends on what this velocity is, what angle that's going to make. So using alpha 2 to break V2 into components, we get a tangential component, so V2 cos alpha 2 is this component, and we're going to call that V sub T2, so the tangential component of V2, and the normal component of V2. So Vn2 will be V2 sine of alpha 2. So we're breaking this velocity into a tangential and a normal component. Now we're reminding ourselves what R2 is here. So R2 is a vector whose center is at the center of rotation, and that points at this point we're considering right now. So that's R2, and we're trying to find R cross V. So R2 cross V2 is going to be the magnitude of R2 times this magnitude, which is V2 cos alpha 2, and that's going to be in the k hat direction. So R cross V will be in the k hat direction. So that's R2 cross V2. And remember, that's what we're trying to find to substitute into the momentum equation. So R2 cross V2 is R2 times the tangential velocity at point 2, and that's in the k hat direction. So next, we want to do exactly the same thing, but at the inlet. So here, the impeller blade will make an angle beta with the circumference of the circle. R1, of course, is the position vector to the inlet position there. Relative to the impeller blade, this velocity is going to be tangent to the impeller blade, and so that'll make an angle beta 1 with the circumference of this circle. The point there is moving at a speed omega r2 in this direction. So that's the velocity relative to the blade. This is the velocity of the blade at that point. We add those together vectorially and we get v1. So that's the velocity relative to a stationary coordinate system. And it makes an angle alpha 1 with the tangent to the circle. Now remember again, beta 1 is a physical feature of the impeller design. It's that angle there. Alpha 1 just depends on operating conditions, what direction that velocity is going. Now we do the same thing here. We break V1, it's not shown here, but we break V1 into two components. A tangential component would be V1 cos alpha 1, and the normal component, not used right here, would be V1 sine alpha 1. So the tangential component is what contributes to the cross product. So R1 cross V1 is R1 V1 cos alpha 1, and again in the k hat direction. So the same as the exit condition. And another way to write that is just instead of V1 cos alpha 1, just V tangential 1. So it just clarifies for us that it's the tangential component of this velocity that contributes to the cross product, R cross V. So we looked at the exit and got R2 cross V2, and we've looked at the inlet and got R1 cross V1. So we can go back to our conservation of angular momentum equation and bring these results in. So here's what we had for conservation of angular momentum: the torque applied to the shaft, mass flow rate, R cross V at the exit, minus R cross V at the inlet, and bring the results in. Notice we're taking the mass flow rate and breaking it up into density and volume flow rate. Volume flow rate is a very common operating parameter for pumps, so we prefer to write this in terms of volume flow rate. And notice also that this is no longer a vector. Here it's a vector equation. Essentially what I'm doing is extracting out the k hat component of it and writing here, because the rotation is all in the k hat direction and the applied torque is in the k hat direction, so we only need to worry about that component. So in here are the results that we got when we did those cross products in detail. So R2 cross V2 is R2 times the tangential component of V2, and then R1 cross V1, R1 times the tangential component of V1. Now we take this and we multiply this result by omega. So we have torque here. If we multiply it by omega, we get the work rate, or the power. And this will be the water horsepower, because this is the rate at which work is being done on the fluid, because that's the momentum balance is being done on the fluid entering and leaving the control volume. So we're just taking this result and multiplying by omega. So not too much has happened there. We just see an extra omega showing up. So this is an expression for torque as a function of those tangential velocities. This is an expression for power as a function of those tangential velocities. Finally, the other operating parameter that we're interested in is head. And so head is the power divided by rho GQ. And if you go back and look when we were talking about pump efficiency and we were defining the water horsepower, it was defined as rho GHQ. So this is just that definition of water horsepower solved for the head. So we have an expression for water horsepower here. So we take this, divide by rho GQ, we'll get the head produced by this pump. So it'll be omega over G, and then the same quantity inside representing the R cross V terms. So these last two equations are very significant. These are called Euler's turbomachine equations. And the basic thing they do is they give us the power consumption of this machine and the head produced by this machine. as a function of these tangential velocities. So we want to spend a moment and look at what is on the right-hand side of these equations. Certainly the power and the head are very useful things to know about this pump. So let's see, what are they a function of? Well, they're a function of flow rate, or at least the power is. Flow rate is there. They're a function of how fast the thing is turning. We've got omega. G shows up in the head, of course. The density of the fluid shows up in here. There are a couple physical parameters of the impeller design. R1 and R2 are just geometric parameters of the impeller. The other two things that are currently on the right-hand side of these equations that are not as convenient are these tangential velocities. So remember what those are. That's the velocity of the fluid entering and leaving the impeller, tangent to those circles relative to the ground. So those are clearly important velocities. They've come into the momentum balance and they are related to these important operating parameters. The problem with them is we really don't know what they are, and they're very, very difficult to measure, of course, because these are happening inside of the pump. So what we need to do is continue to do some manipulation with these basic turbomachinery equations to get them in a more useful form. And that essentially involves revisiting these tangential velocities and getting them in a little bit more useful form so that they're expressed as functions of things that we're likely to know. So in order to do that, we're going to make a key assumption. And this results in something called the design point calculation. So the design point of a centrifugal pump is a particular operating condition where it is generally running at a very high efficiency. So our goal here is to estimate the performance of this pump from its physical and operating characteristics. So the first thing that I'm going to do here is just define what we mean by performance, physical, and operating characteristics. First of all, the physical characteristics of the pump, or at least of the impeller design. So there are 6 of them that we're concerned with. 4 of these we have already seen. So R1 and R2 are the inside and outside radius of the impeller. Beta 1 and beta 2 are the angles that the impeller blades make with the circles at the inner and outer radiuses. We've already seen those parameters. B1 and B2 we haven't seen yet, but we talked about them without giving them a name. B1 is the thickness or the depth of the impeller blades at the inlet, and B2 is the thickness or depth of the impeller blades at the exit. Remember, the pictures of the control volumes that we've been looking at are just two-dimensional slices through the control volume, and the impeller blade in general has some depth or some thickness, and of course those two could be different than each other, and they usually are. So those are all physical characteristics of the impeller. When we build a casting to make a bunch of these impellers, we're figuring out and we're fixing what all of those are. So those are physical characteristics of the impeller. The operating characteristic that we're most interested in here is omega. How fast is this impeller turning? So that's the operating characteristic that we're interested in. And the performance characteristics that we get out of this are the flow rate. How much flow is this going to produce? How much head is it going to produce? And what power is going to require to do that? So those are just the physical, operating, and performance characteristics that we're interested in. So we would really like expressions for these things as functions of these without any velocities inside of the impeller or coming or leaving from the impeller in the expression, because we don't know what those are. We know what all of these things are, and we would like to be able to predict these. So that's what we want to do. Now, going from Euler's turbomachinery equation, so we need to make an assumption because there's too many unknowns in there still. So that's what we're going to do next. So here's what we have so far. We have head as a function of these 2 tangential velocities with operating characteristic here and a couple of physical characteristics. So going back to our impeller, what we want to do is look at the inlet. Now this design point calculation we're doing, and here's where the assumption that defines the design point comes in. The design point is when the velocity enters the impeller at 90 degrees to the circle. Okay, so V1, the orientation of V1, it's not like that, it's not like that, it's perpendicular to the circle. So that's called the design point, where the fluid is entering the impeller purely in the radial direction. Okay, so if we go back to our little sketch there, that means that the thing that we defined earlier as alpha is 90 degrees. So alpha 1 is 90 degrees. That's the definition of the design point operating condition. If a pump is operating off of this design point, then alpha might be greater or less than 90 degrees, but at the so-called design point, it's 90 degrees. Now what that means is that the tangential velocity at the inlet is 0, right? This doesn't have any tangential velocity, it only has normal velocity to that circle. So at the design point, the tangential velocity at the inlet is 0. So going back to our Euler's turbomachinery equation that we have up top here, it means that term is gone because VT1 is 0. It's only true at the design point. But that gets rid of one of our two problems, right? These two velocities, we don't like them in there. So fixing this calculation to the design point gets rid of that one. Now we need to look at this one in detail. So at the exit, let's just recap some of our notation here. So very quickly, that's the velocity of the fluid leaving the impeller blade relative to the impeller blade. It makes an angle beta 2 with the circle. This point is moving at a velocity omega r2, and so we take that velocity and add it to this velocity to get v2, and that's that one. And then this component of it here, the component tangent to the circle, is vt2. Remember, that's the thing we're interested in right now. And this is the normal component. I haven't labeled it here yet, but that's the normal component. So that's just recapping what we've done so far. Now, what we want to do is get an expression for this VT2 in more useful parameters. So that's what we're doing here. Okay, so the next thing to realize is that this angle is beta 2. Therefore, this angle is also beta 2. Okay, that's got to be true. So we can take this tangential velocity, so it's this velocity we're looking at, and it's got to be equal to omega r2, so that's this entire distance from there to there, minus this distance from here to here, right? We're just saying that distance is equal to this distance minus this distance. That's what this is saying. Now, what is this distance right here? What is that? Well, that's V normal 2, that's this one, cotangent beta 2. So that is V normal, so this is V normal cotangent beta 2. Now what we've done here, and it doesn't look like an improvement, but it is, we'll see later, we've got an expression for our tangential velocity that contains geometric parameters r2 and beta 2, an operating parameter, the rotational speed, and vn2. So we've sort of traded this unknown characteristic of the velocity for this one, but it turns out that is a step up. This is easier to figure out than this one is, as we'll see as we go forward here. But that's all we've done so far, is written the tangential velocity as a function of the normal velocity. Okay, well, what do we do with this? Well, we bring it back into our expression. So remember, this is the Euler turbomachinery equation that we're working with. The tangential velocity at 1 is gone, so that's disappeared. the tangential velocity at 2 has been brought in here, and the R2 has been factored out the front here. So this is the result right here that we just did on the previous slide. So that's all good. So this doesn't look that much better but it's got a normal velocity here instead of a tangential velocity. Now we need to turn our attention to conservation of mass. Realize we've been looking at conservation of angular momentum in great detail here, but we also need to apply conservation of mass to this control volume. And in fact, there's some very useful things we can get out of this by doing that. So conservation of mass, going back to our little control volume, remember this is steady state, it's an incompressible flow, and uniform flow assumption. So the normal component of the velocity crossing these two lines is the thing that determines the mass flow rate across them. So if we look at the inlet first of all, the volume flow rate across this line is going to be this component of velocity, Vn1, times the area of that cylindrical surface. So the volume flow rate, which we call Q, is the area, that's that, times the normal component of velocity, Vn1. So let's take a look at this area, make sure we understand it. 2 pi r1 is the circumference of this circle. And B1, this is the first time we've seen B1 show up in an equation, is the length of this little cylinder. Okay, remember that this impeller has some thickness in and out of the screen, and at the inlet that thickness is B1. So 2 pi r1 B1 is the area of the inlet, and then V1 is the speed normal to that surface. So our volume flow rate is given by that. Now we can do exactly the same thing at the exit, of course. So the velocity normal to the surface at the exit is also related to the volume flow rate. Volume flow rate across this line has to equal the volume flow rate across that line. So here we're 2 pi r2 b2. So notice certainly the radius is different, but the thickness of the impeller, its depth normal to the screen could be different. So B1 and B2 are in general different numbers, and then times Vn2. So just a quick reason why we're looking at conservation of mass. Notice we've got this sort of inconvenient quantity in here. Well, it's related to the volume flow rate and to physical features of the impeller. That's why it's nicer to have Vn2 in here than Vt2, because we can write it in terms of things we know, and that's where we're headed. Okay, so what we want to do here is use this to get a connection between these normal velocities. So here's the connection. So we're just equating these two and canceling off a bunch of things that are common. Of course, the 2 pi's are common. So Vn2, which is what we're after here, is equal to R1B1 over R2B2 times Vn1. This is just conservation of mass. Mass flow rate across there equals there. So as the R1 or as the R and B change as you go from the inlet to the exit, the velocity has to change to get the same flow rate. So that's what that is. So that's our conservation of mass equation that relates these two normal velocities. Now what we want to do is look at this quantity here for a moment. Now remember, we're doing a design point calculation here. So at the inlet, the normal component of the velocity is actually V1 because we're doing a design point calculation. So V1 is normal. Remember we said alpha 1 is equal to 90 degrees. That's that angle right there, is 90 degrees at the design point. So V1, or at least the magnitude of V1, is our normal component of velocity. Well, if we take a look at the vector addition of the relative velocity and the omega r1 again, remember that velocity plus this one, they have to add up to the absolute velocity. We looked at that in detail a few slides ago. Well, if this velocity is going to be at 90 degrees to the circle, then that fixes the relationship between omega r1 and this beta. So our normal component of velocity here, that one, has got to be omega r1 tangent beta. Okay? Beta is this angle. Tangent is the opposite over the adjacent. So the normal component of velocity, notice the normal component of velocity is fixed by the geometry, r1 beta 1, that's geometrical parameters, and how fast it's turning. So for a design point calculation, a particular impeller, which fixes that, turning at a certain speed, omega, there's only one normal velocity, Vn1, that works. In other words, if Vn1 is anything different than that, then it's not going to be at the right angle. It's not going to be at 90 degrees. So this fixes the flow rate, because remember Vn1, the normal velocity, fixes the flow rate. So for a particular design impeller, turning at a certain speed, there's only one particular flow rate into this thing that gives you the design point. So that's one of the things that this is telling us. Okay, now what we're interested in though is going back to our equations so far where we have Vn1 and putting this in instead. Because notice now, operating parameter and geometric parameters. That's what we're after. So now what we want to do is take this expression back and substitute it into our expression for head. So what we have so far there is we have the head as a function of a bunch of operating parameters and Vn2. That's what we had when we last looked at this equation. But remember, continuity equation or conservation of mass allows us to write Vn2 as a function of Vn1, and we've just figured out what this Vn1 is in terms of operating parameters. So we'll put that into here and then put the result into there. And what we get when we do that is a very important equation for the design point calculation. So this gives us head at the design point. So we've got this pump running at its design point. What head does it develop? This is the head that it develops. So notice on the right hand side here there is the speed the pump is turning at, and G of course, but everything else is a physical characteristic of the impeller, just a dimension, either R1 or R2, the thickness is B1 and B2, and the impeller blade angles beta 1 and beta 2. So all geometric parameters. We can convert this over to an expression that gives us the power. So the water horsepower would be obtained by taking that and multiplying it by rho, G, and Q. And of course, if we do that, it's exactly the same expression in parentheses here, just Q rho omega squared R2 out front. So these two equations define the head and the power when operating at the design point. And remember, there's just one particular value of flow rate, Q, also. Now that we have these equations describing pump performance at the design point, I want to use them to take a look at something called the blade angle effect. So the blade angles, remember, are the angles that the blade makes with the inside and outside diameters of the impeller at the inlet, beta 1, and at the exit, beta 2. Now it turns out the one that we're really going to be looking at is beta 2. So when an impeller is being designed, beta 2 is one of the most important parameters that needs to be selected. Okay, so let's go back to our performance equations for the design point. So remember, we have the head produced as a function of all these geometric parameters and omega and G. So what we're going to do with this is what we would really like to do is look at the impact of beta 2 in particular on the pump curve. Now remember what the pump curve is. The pump curve is head as a function of Q. So we would like to figure out what this equation tells us about how head varies with Q. Well, the problem we have right now is there's no Q on the right hand side, so it's not very easy to see how head varies with Q when there's no Q on the right hand side. So we need to do a little bit of manipulation of this equation to get it in the form of head as a function of flow, because that's what pump curves are. So we want to know how beta 2 affects the pump curve, we're going to have to get head as a function of Q. Well, let's remember that this volume flow rate is 2 pi R1 B1 times Vn1. Remember, that's conservation of mass applied at the inlet to our control volume. Now we also figured out that this Vn1 is related to some operating parameters as well. So we bring that in, and Vn1 is equal to R1, so there's a squared there now because we already have an R1, times omega tangent of beta 1. So remember when we were looking at conservation of mass, we looked at that, and that has to be the connection between Vn1 and those parameters. So our volume flow rate is 2 pi R1 squared B1 omega tangent beta 1. Now, if you take a look at this term here, you can see that most of this stuff is up there. So we're going to be able to get rid of a bunch of this and get a Q in its place here very soon. Well, to make that a little bit more clear, we're just going to take this 2 pi and move it underneath here because there's no 2 pi up in there, so we need to get rid of that. So now Q over 2 pi is R1 squared B1 omega tan beta 1. Well, take a look at this. We've got R1 squared B1. We've got omega out here that we can bring in, and tangent beta 1. So we're going to be able to get rid of a bunch of this stuff and just call it Q over 2 pi. So that's what we do next. So that's what's happened here. Notice we've taken this term out front, omega squared R2 over G, and distributed it into these two terms. So this first one becomes omega squared R2 squared G, and that's actually a very important term we'll see in a moment, minus, now we have our Q over 2 pi here, Q over 2 pi taking the place of all of that stuff. Okay, so what's left is omega cotangent of beta 2, that's still there, 2 pi B2 G. So if you notice, we now have H as a function of Q, which is what we set out to see. Notice everything else in here is either geometric or operating parameter. So omega, how fast we're spinning the thing. G, of course, acceleration due to gravity is in both of these terms. R2, B2, beta 2, those are all geometric characteristics. So we've got H as a function of Q. So this is an approximation, at least, to the pump curve because it's H as a function of Q. Now you'll notice it's actually an equation for a straight line. H is just linearly related to Q. So we're going to sketch some of these and investigate this a little bit. Now remember, what we're after here is blade angle effect. So we could write this whole equation just as H equals A minus BQ. And of course all of that stuff is A and all of this stuff is B. So one of the important things we can get out of this is an estimate of the shutoff head. So for Q equals 0, the head is equal to A. So this is a very quick way to estimate the shutoff head of a pump. Omega squared R2 squared over G. So based on the design point calculations, an estimate of the shutoff head is that. So that's the first sort of useful thing that we get out of this investigation of the blade angle effect. However, that doesn't tell us anything about the influence of beta 2, the blade angle, on the pump performance curve. So for that we need to take a look at this term. So here's what happens. Well, if beta 2 is less than 90 degrees, and in fact that's how I've sketched them all up to this point. So beta 2 has always been less than 90 in the sketches we've seen. So for beta 2 less than 90, the cotangent of beta 2 is a positive number. So that means that B is going to be greater than 0. So remember what B is. B is this quantity here. So if that's positive, then that quantity is positive. So omega certainly is, B2 and G are all positive. So the sign of that B, which I've put in a red box there, is governed by beta 2. So beta 2 less than 90, cotangent of beta 2 is positive, and B will be bigger than 0. So beta 2 less than 90, those are called backward facing blades. So a backward facing blade has a value of beta greater than 0. If beta is greater than 90 degrees, and we'll show what that looks like in a moment here, but if beta is greater than 90 degrees, the cotangent of beta becomes negative. So that means this B is less than 0. So a characteristic of forward-facing blades is that this B is less than 0. And remember what role B plays in this equation. It's the slope of the H versus Q line. Now there's a dividing case between these two. If beta 2 equals 90, the cotangent of 90 degrees is 0, and B is equal to 0. So the head will just be a horizontal line at the value of A, because B becomes 0. So let's take a look at this on a pump curve. So we're looking at head versus Q. So backward facing blades, which is what I've shown so far, so this is a sketch of a backward facing blade, has beta 2 less than 90, B is positive. That means the slope of the pump curve is negative. Now we haven't seen a pump curve so far that is just a straight line, and in fact real pump curves are not a straight line. This is just a linearized approximation to the pump curve based on the design point calculation. But it does tell us some fundamental characteristics of blades. So beta less than 90, backward facing blade, slope in this direction. If beta equals 90, this is what the blade would look like. It would touch the outside circle at 90 degrees, okay, perpendicular. So that's a flat blade, and it would have a horizontal or a slope equals 0 pump curve. A so-called forward-facing blade, which is a case we haven't seen sketched. Remember, all of these things are turning in a clockwise direction. So this is now a forward-facing blade because beta 2 is greater than 90. Well, that will result in a pump curve with a positive slope near the design point. So this is the blade angle effect. Backward-facing blade, negative slope to the pump curve. Flat blade, flat pump curve. Forward-facing blade, actually a positive slope to the pump curve. So increasing flow produces increasing head. Now, in reality, most centrifugal pumps are built with these backward-facing blades so that the pump curve looks like this. Now, there's a very good reason for that I want to talk about next. Occasionally there might be one designed like this, but for very special applications. Most are like this, and here's why. So now we're looking at a real pump curve that has some other effects going in that the design point calculation can't take care of up here at high flows. But if we had a pump designed with forward-facing blades, then there would be a region of the pump curve here that would actually have a positive slope. So that's what this pump curve is intended to show, a forward-facing blade design. So that's all good. That's the pump curve. Now remember, one of the main things we can do with these pump curves is we can plot them on the same axis as a system curve. So let's say we take this pump and we hook it up to a piping system whose system curve is characterized by that. And remember, these are parabolas as well. So this is the fixed system pressure, and then the variable system pressure is determined by how quickly that rises. Well, where these lines cross is our operating point. Now, see one problem that we have when we have a positive pump curve like this, and this example illustrates that. Is the operating point here, or is the operating point here? What this is telling us graphically is that if we take a look at the equations for this and we equate our system curve to our pump curve, which is the typical way to find this operating point, we solve for where they intersect. Well, this actually has two intersections, and in fact it has a whole range of flows here where they're very, very close together. So what will happen if we take this pump and hook it up to this system is it will be very, very unstable. In fact, it could just spend its time jumping back and forth between these. The flow would be changing very erratically between these limits because it's essentially happy with either one of these solutions, and little disturbances will make it jumping back and forth. So this is a very unstable situation, and for that reason most centrifugal pumps are designed with backward facing impeller blades, not forward-facing impeller blades.